And then now let's look at the final example problem. This has to do with elastic potential energy. The way that I'm going to do this is, well, we got the two scenarios again, just like the previous one. And so what we want to do is we want to look at both of those scenarios separately. So let me go ahead and draw what we have. We have a spring that has a force constant of 500 newtons per meter. So it takes 500 newtons to stretch or compress the spring 1 meter. And then it asks, what is the potential energy stored in the spring? So when the spring's at rest, we'll say it is that far away. Now in scenario A, I'm actually stretching the spring 4 centimeters. And in scenario B, I'm actually compressing the spring 3 centimeters. So let me go ahead and label this. So from that location to that location, we're going to say is 4.00 centimeters. And then from this location, let's undo that. Hopefully it'll just let me draw it. From this location to there is going to be 3.00 centimeters. Okay? I know that K is going to equal 500.0 newtons per meter. And then my delta X's are these 4 and 3 centimeters. The equation for elastic potential energy, so that's PE equals 1/2 my spring constant K times my X squared. And so that's my change in X position, or my compression, or my stretch. So let's look at scenario A. That's this one. And B, that's that one. In A, X, so here's A, X equals 4.00 centimeters. Now, centimeters is not the standard or the base term for that we like to see our lengths in, and so we need to go ahead and convert that to meters. And in order to do that, I need to divide by 100. So it's going to give me 0.0400 meters. So I just plug that in. PE equals 1/2. My K is 500.0. And my X is 0.0400, and then it's going to be squared. So that's my plug-in. And my answer that my calculator gives me, will let me go ahead and pull up my calculator. Clear that all out. And then now I want to go ahead and type this in. So I get 0.5, which is 1/2, times 500.0 times 0.0400, and I want to square that. So I'm going to go ahead and click on the square and then hit equals. And so I get my answer is that my gravitational potential energy equals, and let me go ahead and verify what that is, 0.4, and in this case I have 4 significant digits and I have 3 significant digits, so I'm allowed to keep 3. So I need to at least have 3, so 0.400, and then the units are joules. All right, and let's go ahead and highlight that. Get out of here. Okay, so there is my answer to question or scenario A. Now let's look at scenario B. On scenario B, in this case, my X equals 3.00 centimeters. Now, I know it's going to the left, and we said left is negative, but once again, the energy is a scalar. And if we look at this equation, if I put a negative number in for X, well, I'm just squaring it anyway, and a negative times a negative just gives me a positive. So let's go ahead and plug in. PE elastic equals 1/2 my spring constant 500.0 times my X, which is Instead of 3 centimeters, I need to once again divide that by 100. So 0.003. Oh, one too many zeros there. 0.0300 meters. So let's go ahead and put that in here like that. 0.0300 meters squared. So let's go ahead and pull up the calculator. And now let's move out of our way over here and clear it. And I'll go ahead and type in 0.5, which is the half, times 500.0 times 0.0300, and I want to square that. So I'm going to click the square button and then the equal button. And so that gives me my answer of 0.225. So my answer, PEE equals 0.225. And then my units of this are joules. And I have 4 significant digits here. I have 3 significant digits there. I'm allowed to keep 3, which is what I have. And let's go ahead and highlight that. And there we go. And so that's the answer to example problem 3. And this is how we work the elastic potential energy equation.